Good morning, everybody. In today's lecture, we are going to complete the current lecture, which is lecture 1, on what we mean by the problem situation, and then I think we'll have a chance to go on to the next lecture, which is really the first lecture on systems formally. Now, the problem situation, the lecture on problem situation, corresponds in some part to the chapters in the book, but not exactly. Our purpose of introducing this lecture at the beginning is to just clarify the idea by which we mean a problem situation. This is something which is a familiar concept to you from your other courses on operational research, and we have described, for example, the components of the problem situation, and most importantly, the people involved in a problem situation are known as the stakeholders, as we have seen last time. And we can identify several different roles that the stakeholders play in a problem situation. Some of them act as owners of the problems, others as users of the problem. Then there are the customers and the affected, and finally, there is the consultant or the analyst, okay? And we have described what each of these roles mean. The last point we were making was that you should not identify a person with only one of these roles. These are not persons but roles, and they can be, for example, changed during the during the course of inquiry, or maybe the same person can take on the role of 2 or 3 stakeholders. For example, if you have a small type of project in which the decision-making problem is not too complicated, then the problem owner can also be the analyst. And in fact, the solution proposal that he produces at the end of the inquiry can affect himself. So the same person can be all of these, can play all of these roles, okay? So that was the last point. Role definition is important. In the case, let's take some examples from the cases in the book, the breast cancer case. In this one, if the screening project for breast cancer is initiated by the Minister of Health in the country, if the health minister initiates a project, the concern will be about effective allocation of funds and priorities and trade-offs and costs, and the entire health system will be of interest. In this case, for example, the problem owner will be the health minister, so he will have authority to allocate funds to this project. But of course, it will be difficult for him, as these comments indicate, because the Minister of Health in a country has a limited amount of money available every year from the budget, and he has to, or she has to, allocate this budget efficiently to many requirements of health in the country, and this is just one of the projects. So there must be many trade-offs, and the priorities have to be taken into account. And the main concern probably will be costs and effectiveness. In the same problem situation, if doctors or women's groups initiate the project, then concern will be about minimizing the incidence of cancer and fatalities, not directly over costs. The problem users in this case obviously are the people who will be responsible for the implementing of the screening, the operators of the mammography machines, other health personnel, etc. And they may be, it may be necessary to persuade and train them unless they sabotage the implementation. I mean, sabotaging the implementation of cancer screening is not very plausible, but it's just a possibility because people may not like, for example, extra work, etc. So these roles may also be reassigned if playing one or the other role by one of the stakeholders can change concerns about efficiency and efficacy. Okay, so roughly this is what we mean by a problem situation, and these are the stakeholders that are involved in each and every problem situation. Now, if you pass this course, okay, next year you will be taking the systems design courses we have, 2 courses, in which you will be asked to conduct an OR research, an industrial engineering research in a real world situation in a business company or any institution such as that. And then when you start your projects in those in next year, hopefully, the first thing you have to do is to look at the problem situation. Okay, so please remember next year all these lectures and courses, or the readings that you are assigned in this course, and try to make use of them deliberately, not just by remembering ideas and concepts and making sure that they help you there, but just by looking at the definitions, these lecture slides, and trying to implement and repeat them in the real situation. Okay, this is an advice that we give every year, but what happens is that when you go to the final year and start with the projects, we notice that students don't remember to look back on these notes. Please make sure that you keep these in mind. For example, in the problem situation, the first bit of inquiry next year will be who are the problem owners, who are the problem users, who are those going to be affected from these, etc. So this is quite important. Now, in order to make sense of such complicated, complex actually, we shall be doing complexity after the next lecture, complex problem situations, is that there is a lot of detail, and it's usually not easy to keep all these in your mind and remember everything and every time. So a very, very useful method to overcome this initial confusion is to make use of graphical devices. Now, normally engineers use a lot of graphical devices, but I think the classical engineering disciplines such as mechanical engineering, etc., you make more use of graphical devices than we do. So our students are not very very successful in using these devices. My advice to you is, we are going to learn a few devices, such devices in this course, is just to pay attention and make an effort to understand and make a habit of using these. Now we are going to look at only 2 types of graphical devices, mind maps and rich pictures in this lecture. There are others, as we shall see in the following chapters. So these mind maps and rich pictures are useful as a first step in setting down and representing our perception of the problem situation. How do we perceive the problem situation? What do we see there when we observe the situation? So if you put this on a drawing, it will help. Now, all aspects of a problem situation are mapped on a freestyle diagram with or without pictures. All aspects you can put on paper, including as much or as little detail as necessary. The detail to be represented in the diagram is something to decide for you. You can decide to include a lot of detail or not too much. The drawing that you make should be independent of any particular Weltanschauung, but as a joint product of conflicting views of the situation. Now, what this comment means is that when you are making these diagrams, don't try to draw these diagrams from your own perspective or from the perspective of the top manager involved in the problem situation or one of the engineers, okay? the perceptions of all of these people should be represented on the diagram, not from one worldview or Weltanschauung, but including all relevant Weltanschauung. Of course, these different perceptions of the problem and in the problem situation will sometimes conflict with one another. What ought to be done according to the top manager will not be the same as what ought to be done with respect to from the point of view of one of the engineers or one of the workers. So all these conflicting views should be included. One important point in making these first diagrams is you should not try to identify any systems. The system concept is so powerful in our curriculum that all students try to identify some systems all the time. Obviously, you will do that later on, but at this step, when you are drawing a mind map or a rich picture, you should not try to identify any system at all. So this is just freestyle drawings. And these drawings should not be drawn at the beginning once and then forgotten, but they should be redrawn as many times as necessary. The primary use or usefulness of these drawings is, of course, firstly, they help you to perceive the whole situation easily. But more important than them, perhaps, is that they will act as a communication device. You will make a rich picture of the situation, and then you can show this to people, to the stakeholders, the problem owners, and other people in the problem situation, and you can tell them, look, this is how we see the situation. Do you think this is correct? Do you think this is complete? Or are we missing something? Or is there any unnecessary detail here, okay? So this sort of communication with people that you're going to work with in the projects is facilitated immensely if you have such devices ready with you. Now, let's look at a mind map, first of all. This is a mind map from the textbook. As you can see, the mind map includes a collection of a lot of comments, and these comments are not of the same type. For example, some are questions, some are adjectives, some are actions, etc. So mixing all types of entities like this in the same diagram is permitted here. Later on, in following chapters, we are going to make other diagrams, like influence diagrams, flow charts, etc. In such diagrams, if you have the same shape, if you are using a shape, for example, as an entity in a diagram, the shapes, the same shape, if you use one type of shape, it should include all one type of entity. For example, questions only, decision points, or actions only, or materials only. You should not mix them together. Here, you can mix everything. This is the case of a person. The problem situation here is very simple. There is a person who goes to work every morning, and he has to decide how. For example, he can take a bicycle, or he can take the bus, or he can go with her car. So in the morning, she has to decide which mode of transportation she is going to use. She has to go to work, and the question is which mode. Mode means mode of transportation. And the questions are bus. Shall I take the bus? If she takes the bus, she has written there, takes too long. Oh, this is one point about taking the bus. It takes too long because the bus goes in a roundabout way and makes several stops. What's the other alternative? The other alternative is to take the car. But the car is not friendly to the environment because it puts out a lot of carbon into the atmosphere. So it's a concern for this person. Another concern is that if she takes the car, she will not be getting any physical exercise. She'll be just sitting in the car. It's similar for the bus, but maybe In the case of the bus, she has to walk to the bus stop. So there is some exercise involved, but in the car, there's no exercise. But there's also an advantage. It's faster and maybe it is safer, okay? Finally, the other decision is the bicycle, cycling decision. If she cycles, the disadvantage is it's dangerous. Cycling is not very safe. But it is healthy. It's environment friendly. And she has to have ample time for cycling, of course. Deciding about which mode also is affected by what the weather is like. For example, if it's raining, then probably she won't be able to cycle, etc., etc. So this is the sort of very simple mind map, which pictures all the alternatives and her thoughts about these alternatives, weighing the disadvantages and the advantages, drawn freely on a diagram like this. There's another box here. It says, I need physical exercise. Well, actually, she wants to keep in shape. She wants to look beautiful. And for this, she has to have exercise. And the exercise also has to be enjoyable. Maybe then she will be cycling through the park. Even if cycling through the park, there is presumably a park, which will make her journey longer, but it will be more enjoyable, etc. So she has also included these. So this is just a mind map, and as you can see, it is completely freestyle. The point is that all the alternatives and their implications are mapped, so she can see all of them now. This is a rich picture of the same situation. As you can see, the mind map is simpler to draw. The rich picture is, well, it's prettier. It looks much better, maybe. It includes pictures and diagrams and everything, as you can see. And in this case, the decision maker is pictured as a man. So again, this is the same situation, as you can see. Taking the bus is one alternative. He has drawn there a clock indicating that it will take too long with the bus. Also, he has included the cost of taking the bus, the fare. Fare is the money you pay for the ride. It's $2. That's the alternative for taking the car. It will make a lot of pollution, etc. And he will be getting fatter because there will be no exercise when he takes the car every morning. He is dreaming about looking like that. Instead of a fat person, he is dreaming about looking very fit and nice, and etc. You can so see all the considerations of the mind map. Also here, there's a cloud there. If it makes rain, he has written, oh no. So you can do all of these things. I think a rich picture is better to start with. Maybe you can start with a mind map, but you should make a rich picture. We ask the teams in the systems design course every year to make a rich picture of how they see the problem situation. You see, formulating a problem that you can attack with the quantitative techniques that you have learned in the system design course takes several weeks. The students cannot start the problem formulation and making sure what you are going to deal with takes several weeks after the start of the project, during which time such graphical devices become very, very useful in order to be able to formulate the correct problem later on, okay? Now, what should we include in these diagrams? They should include elements of structure. You see, we make a distinction for the first time between what we call a structure and what we call a process. You should understand these properly. What we mean by structure is stable or slow changing aspects such as buildings, equipment, products, rules, advantages, difficulties, etc. Anything that cannot change very quickly, any entity that cannot change quickly in a problem situation is a structural aspect. It's a structural entity. Okay? Things which change easily or relatively easily or quickly are called processes. Dynamic aspects that change fast, such as activities, material flows, information, etc. All right, is this clear? Now, let me comment at the very beginning here. The dichotomy between structure and process will be relevant later on several times, and we are going to maybe use sometimes different terms to indicate these, like levels and flows, etc. But let me just if X is a structure, if we indicate a structure with the variable X in a mathematical model, what do you think the corresponding process will look like in mathematics? Anyway? Yeah, it will be usually, not always, it will be usually this. Okay? The time rate of change of X. Can you give me an example for a structural variable and the corresponding process variable from industrial engineering concepts? For example, could this be the level of inventory? It could. What would be this then? Replenishment from stocks or withdrawals from stocks, for example. For example, if this is capital, the capital invested, what should this be? Capital stock? What is the rate of change of capital stock? What do you call it? Investment. Investment. You see, you have a firm, you have a lot of capital invested in the firm. That's your capital stock. Buildings, materials, inventory, etc., etc. This year, you decide to increase your capital stock by making new investments. So if this is your capital stock, then investments is the rate of change of that. So, I mean, of course, if this is positive, it is investment. If this is negative, then it is, what do we call if it is negative? Depreciation or something like that, okay? Withdrawal from, or retirement. You retire some of the machinery from your portfolio, etc. So the idea is, please keep this in mind, okay? Structure and process. I'm not saying that always structure is if structure is such a variable, then its time rate. This is not 100% and true in all cases, but generally it works like this. Other terms that sometimes are used associated with these are stocks, capital stock, and flows. Stocks and flows. Usually in economics they use these terms a lot. Okay, so structures and processes. You should try to indicate all structures and processes in your diagrams. Of course, then these have to be related to one another in some way. So the relationships between structure and process and the consequences of these relationships should be indicated. The facts or data are also, we have learned what we mean by data, information, knowledge, etc. In the first lecture. So the data and the information, which we call facts, should also be shown in these diagrams. But you can see that these facts come in two classes, soft and hard. What do you mean by soft data? And what's the difference between soft and hard data? Yes, usually hard data is something that you can measure and put in numbers. And soft data is difficult to put in numbers. And you can see an example of this here. For example, the man over there with a belly, the fat man, does not have a very cheerful expression. He looks sad. The expression, his facial expression, is soft data. The man at the top also has an expression who is wondering, he's thinking. So that's soft data. Okay, soft and hard data. Well, you can put any other aspects that will facilitate learning and discussion. Discussion, of course, is both among the members of the project team and also with the stakeholders. One warning about making such diagrams could be that you should not use too many connectors. When students are asked to draw these diagrams, they like very much to connect everything with arrows. So they start to draw arrows. You should not use too many such connectors, etc. Okay. Well, I have added here, these are from several years ago. In this course, we sometimes ask you to draw these as a classwork or even midterm question, and these were drawn by some teams, okay? You can read about the an example in the book, I think in the exercises of the chapters, a blood bank situation. You know, a blood bank is a place where they keep blood, which is necessary for operations and other things in hospitals. And the operation of a blood bank is very complicated. In our department, we have conducted, I think, several projects on blood bank operations, both professionally and also as student projects concerning Kızılay's blood bank operation. It's very important. So this is just a rich picture of a blood bank operation. You can study this on your own. This is another rich picture drawn by the group Mickey. Mickey. The other group was named, I don't know what. So these two groups of students have come up with two different rich pictures of the same problem situation. So I have just put them here just to help you understand what we mean by a rich picture and how different groups of students have come up with different rich pictures of the same situation. So that's the end of our introductory lecture on the problem situation. And we can move over quickly to lecture 3, which is about systems and systems thinking. So now, little by little, we try to understand what we mean by systems and systems thinking formally. This is an important lecture, and also the following lecture will be on complexity. These two lectures are of fundamental importance in our course. Introduces basic concepts of systems and systems thinking. So these are the questions that we are going to try to answer in this lecture. What's the method used in science? What do we mean by science and scientific method? And should operational research industrial engineering use the method of science? So that's the first important question. Object-object duality, decision-making in complex situations. We shall discuss concepts of efficacy, effectiveness, efficiency. And later on, we are going to answer the question what a system is and what kinds of systems there are. So let's start with this very fundamental question. What method is used in science? Let's go way back in history to the time of the ancient Greeks. As you know, Aristotle and his teacher, what's the name of his teacher? Yes? Plato, right? Eflatun in Turkish, Plato in English. Plato and Aristotle are very important in the history of Western thought and also in human history as the two of the greatest three philosophers, probably. So Aristotle, Plato actually is the person who came up with the concept of a concept. For example, he defined the concept of a circle, a perfect circle, or a triangle. Now, if you look at nature, there's no triangle, there's no circle. There are things that look like circles, or that look like triangles, but he perfected these and made an abstraction of real world phenomena. If you make an abstraction of real world phenomena, you have a concept. So Plato is the father of conceptual thinking and rational analysis. His student Aristotle placed more focus and emphasis on what happens in the real world rather than just on what takes place in our reason, in the mind. So Aristotle can be thought of as the father of observations and experimentation. Okay, so this slight difference in perspectives of these two philosophers have defined 2,000 years of philosophy. So anyway, Aristotle looked at the world as a living being. Parts of the world could only be understood in terms of their relationship with each other and with the whole. So he thought that the whole universe was a living entity. This is actually a systemic or a holistic view. This is a systems view. You see, Aristotle, more than 2,000 years ago, actually was looking at the world from a systems perspective. The word holon and holistic also means systemic. What do you mean by systemic? Systemic means having the property of being a system. Systemicity, for example, if we derive a noun from systemic, is the property of exhibiting the properties of a system. Systemic is important because you should not confuse it with systematic, as I told you. Systematic doesn't mean anything at all in our course. Systematic means just orderly. It doesn't mean having the property of a system. If you want to say that something has the property of a system, then the adjective to use is systemic or holistic. Holistic is the same word, means the same thing. This is a systemic view of the world, and it's also a teleological view. So teleology is important as a piece of general knowledge. It's a doctrine that says there's a purpose to everything. Okay? If you view the world, you will see many phenomena. And if you try to put a meaning to any one phenomena under observation, and you do this by looking for a purpose, and you believe that if there is something, there must be a purpose to that, the view you are taking is a teleological view. Okay? Teleology is the doctrine that says there's a purpose to everything. It explains phenomena by the purpose they serve, rather than by postulated causes, by taken for granted causes. Okay? So Aristotle had this sort of view. And this sort of thinking dominated Western thought for more than 2,000 years, even though, of course, they didn't call it systems thinking at the time. This period, which extended for so many years, came to an end at the period which we call the Enlightenment, in Turkish, aydınlanma çağı, which marked the beginning of modernity. or the age of reason. Now, the concepts enlightenment and modernity are sometimes used interchangeably, but enlightenment refers to what takes place in the human mind, probably, and modernity is the material result of this. Okay, so the age of modernity can be understood as the age in which we make decisions through reason, by reference to our own reasoning capabilities. What would be the other alternative? Now, of course, we are used to make decisions on our own by human reasoning. The other alternative, of course, would be to ask somebody. To ask somebody, okay? So up to the Enlightenment, people, when they were making many of the important decisions to be made, they were referring to some higher authority rather than making their own decisions, okay? What's this higher authority, do you think? What is it? Usually, they were the religions and some mystical authority like that. Now, modernity started with the emergence of modern science. So modern science goes together with enlightenment, and it has created modernity. And especially empirical sciences. When teleology was replaced by Cartesian mechanism, based on the philosophy of René Descartes. You have heard about René Descartes. He is the first modern philosopher who has, for example, talk about Cartesian coordinates in algebra. Cartesian is the adjective for, Latin adjective for Descartes. It comes from Descartes, Cartesian. Cartesian mechanism was the first influence on which created modernity. Most importantly, of course, it's the work of Newton, Isaac Newton, which has defined modern science. It has defined what modernity is, and it has led up to the formulation of the ideas of enlightenment. He died in 1727, and he developed, as you know, mechanics, the laws of motion and gravity. To do this, he invented calculus, actually. His work actually shaped the modern world. It determined how we live and understand the world. So Newton's influence probably is the greatest influence on humanity by anybody, any political leader, any thinker, any scientist. I think Newton has had the greatest influence. Now, we like to say that we perceive the world from the Newtonian perspective. What do we mean by that? The Newtonian perspective of the world is reductive rather than holistic. So there's a break from systems thinking, the traditional systems thinking, which we can call teleology. There's a break with Greek teleology, starting with the emergence of modern science, culminating. Of course, modern science did not start with Newton. It started much earlier with Galileo Galilei, etc., etc. But the flowering, the culmination, I think, occurred with Newton. And his perspective assumes that analysis is the means to gain knowledge. When we go on to the next lecture on complexity, I will give you some notes that I have written myself, and also a reading in which all these ideas and developments will be detailed much better later on. But at the moment, this is sufficient. Reductionism is the reduction of all phenomena to simple unidirectional causal relationships between variables rather than interactions that can only be explained in terms of the functioning of the whole. Now, since you have read the article by Ekhoff, by now you should have read it, You are familiar with these concepts, so reductionism. Let's look at the definition of reduction from the dictionary. It's the practice of analyzing and describing a complex phenomenon, especially a mental, social, or biological phenomenon, in terms of its simple or fundamental constituents. So reduction, do you understand the relation or the difference between analysis and reduction? They are very similar, okay? Analysis means, of course, breaking a whole into parts. Why do we do that? Because it is difficult to understand the whole, and we hope that if we divide it into smaller parts, we shall be better able to understand each part. And of course, the idea in analysis is that in order to obtain knowledge about the whole, we can combine the knowledge we obtain of the parts. And the combination of these knowledge of the parts will give us knowledge of the whole. This is the idea of analysis. Reductionism, of course, is similar, but reductionism is slightly different in the sense that it says that breaking into parts should go to the limit. In analysis, you don't have to go to the limit. What's the limit in reduction? The limit in reduction are the subatomic particles. Just in a way of thinking. For example, if we want to understand, for example, a phenomena of psychology, somebody is sad. He is suffering from something, he is sad, he is not happy. And if we try to understand why he is not happy by using a reductionist method, what we would do is that we would take this problem of psychology about happiness or sadness and transform it into a problem of biology. Why? Well, a human being suffering is a biological entity. So we can use the methods of biology to find out why he is unhappy through identifying the biological processes taking place in his metabolism. But biology can be transformed into a problem of what, do you think? Chemistry, probably. Because biological organisms are chemical compounds in the end. And chemistry can be reduced to physics. So all problems can be reduced to physics. And not only physics, but in physics, of course, the idea of reduction is to find something which cannot be divided. Until we are able to arrive at such an impossibility, we keep on dividing. That's what we mean by reduction. And in physics, for example, this was thought to be the path to reality. Reality would only be discovered and understood by dividing and keep on dividing. So first came, for example, the atom, and then people understood that atom was not indivisible. It could be divided into the electron and the nucleus. And the indivisibles were thought to be the electron and the nucleus. Then later on, they discovered that the nucleus could be divided into the protons and neutrons. And then electron, the proton, and the neutron were thought to be the indivisibles. And this kept going on and still going on, and now it's probable that there's no end to division. So particle physics, I think, has lost its importance in the last 20 or 30 so years. They are still trying to divide particles. There's a project in Europe, as you know. There's the big cyclotron in Switzerland and France, where they are trying to smash these particles even further, etc. Anyway, so reductionism is analysis to the end. Okay, so that's the Newtonian perspective. This is a paradigm. We can call it the Newtonian or the mechanistic paradigm. It dominated science until the middle of the 20th century and is still alive. Even in everyday language, it is still alive. What do we mean by a paradigm? Paradigm is an important concept again. The concepts that we introduce, several concepts that we introduce for this course, are technical concepts, obviously, understood within the context of this course, but they also apply to everyday life. So all these are important not for this course, but for you to understand the world outside industrial engineering practice. Paradigm is used a lot, I think in Turkish also. Paradigma değişikliği falan diyorlar. A paradigm is a worldview underlying theories and methodology of a particular scientific subject. So it's similar to what? What other concept is similar to this? What's the other concept which is similar to this? Which is not scientific? There it says worldview, huh? Weltanschauung. The concept of a worldview, when it is formal, when it is it is used as a reference by a scientific community, it's called a paradigm. There's another alternative definition. A paradigm can be defined as a set of shared and formal assumptions about the nature of reality and our knowledge of it. Usually a paradigm is something that you do not question, you do not criticize, you accept it. So the Newtonian paradigm has been accepted. And this is articulated in this paragraph I took from Jackson. The power of the Newtonian paradigm is described as follows. Jackson says, I took this from Jackson, but Jackson has taken it from somewhere else, I don't remember. Each of us lives and works in organizations designed from Newtonian images of the universe. We manage by separating things into parts. We believe that influence occurs as a direct result of force exerted from one person to another. We engage in complex planning for a world that we keep expecting to be predictable. And we search continuously for better methods of objectively perceiving the world. These are the ideas of the Newtonian paradigm. You have studied Eickhoff's article, and he articulates all of these ideas in there, also in mechanistic systems, for example. Our systems is the perception of systems from the Newtonian perspective. Newtonian thinking emphasizes cause and effect thinking in contrast to systems thinking. It is a hard view of the world and is based on the assumption that objectivity is possible. The key concept on this slide is objectivity, objectively. Because the idea is that if we are going to discover reality, our discovery must be made objectively. The concept of objectiveness. I'm not going to define such difficult concepts. We don't want to make the course too cumbersome or too detailed, but you can imagine what we mean by objectively. It means independent of personal biases, distortions, and things like that. Impartial could be another word, but objective is a much stronger concept, okay? So let's continue tomorrow with objectivity.